Challenge problem number 12, strange motion.
You accepted.
Wow.
Hi, my name is Justin, and I'm going to present for the all-nighter team on number 12, strange motion. So the problem statement is here. Sprinkle small floating particles on the surface of water in a bowl. Bring a strong magnet above and near the water surface. Explain any observed motion of the particle. And for the focus, we're going to focus on what particle material allows the particle to move. What does a magnet create? How and why does a magnet create particle motion? And what parameters affect the observed motion of the particles? Alright, so during my presentation, I'm going to go over some preliminary experiments, some explanation of those phenomena, some theoretical models, and some experimentation and discussion, and I'll end with some conclusions. Alright, so first of all, this is a demonstration of ferromagnetic material. In this case, it is iron powder, and it is clearly attracting to the magnet that is suspended above and near the water surface. So you can see it's iron particles moving towards the magnet. And then moving on. Alright, so as some general observations, ferromagnetic materials attract and move across the surface towards the magnet. And then, however, paramagnetic and diamagnetic particles do not move because of the intrinsic properties of magnetic attraction properties. And then also some detailed observations is that particles orient towards the magnetic field almost immediately. That means its alignment is almost immediate. At the same time, particles tend to align and stay together when in motion. Since different particles they get induced by the magnetic field, so therefore sometimes they may stick together when in motion. And also particle speed also depends on the proximity to the magnet. So if you have a coordinate of x and y, the particle speed would depend on that. And then over here we tested different materials, ferromagnetic materials, paramagnetic materials, and diamagnetic materials. And then just as some demonstration, you can see that paramagnetic and diamagnetic materials do not move because of their properties. I can explain why that happens later on as well. Okay, and then some basic explanation for why ferromagnetic materials move towards the magnet is because of their intrinsic magnetic properties, such that their magnetic domains within their material, the particles themselves, they orient towards the external magnetic field. And then it's because of the variation, the non-uniformity of the B field of the external magnet, the permanent magnet, that creates the particle motion and it attracts the particles towards the magnet itself. Alright, and so I'll move on to some theoretical models. First of all, I mapped the magnetic B field on the surrounding of the bar magnet I'm going to test over here. Alright, and as you can see, I mapped the Bx, By, and Bz to get the actual B field vector. So I mapped all three vectors to get the actual B field at different locations in a 3D coordinate system. And as you can see over here, that's the relative magnet location, and you can see the B's rising towards that, meaning the value of B is high as it gets closer to the magnet. Alright, and so this is some generalization I made for the magnetic B field. As you can see, since the particle is moving on water surface, we have to account for the B in the x and y coordinate. Alright, so this is some calculations for that, and you have to do the cosine of that to get the actual B in the xy direction. Alright, and then also we have to assume that the particles initially do not align with the magnetic B field, because sometimes they're in random orientations, and then so you have to account for that. And so to account for that, we use we use the torque equation over here. And so as you can see, we generalize each particle as an ellipsoid, so it's kind of like a sphere, but then with a longer radius at one portion, like that. And then we use the negative magnetic moment times V sine theta. That is the external B field's torque on the particle, and then also the L/2 times crossed by F of drag is the water drag when the torque generated by the water drag. And as you can see over here, theta, this function slowly decreases and oscillates between the magnetic alignment direction. And then for our calculations, we deem that 10% of the original theta naught is the where we define that the particles align with the magnetic field. And then for that calculation, we got 0.07 seconds. And then with our experiments, we concluded that, okay, that is automatic particle alignment. Yeah, and so further on, to get force, we have to get potential energy first. And then so by doing that, we use the formula potential energy equals to the negative magnetic moment times the external B field. And then through some derivations, you can see that we can either conclude with making the magnetic moment of the particles constant or varied by B. Further derivations of how the magnetic moment of the particle is proportional to the B over here, as seen in the K plus CB, can be shown later if the opponent wants to discuss that. Okay, and then to get the force, we use the equation F equals to the negative derivative of the potential energy with respect to its X or Y direction. And using a kind of plot like that, we use the local gradient to find at each position for example, you're using the potential energy over here and the potential energy over here to actually get the linear gradient in between to get the actual force. Okay, and then so using Python's plot, we determined that our model using the magnetic moment of the particles that is varied by B is the better fit. And as you can see by the better fit over there on the right. And then with the constant magnetic moment, it doesn't work out very well. So our model is based on the magnetic moment is determined by B. So moving on to some experimental discussion. First of all, we sprinkled iron powder into a glass tank filled with water. Okay, and then we dropped the bar magnet into a secure location above and near the water position, so that we can measure the particles' attraction motion when the B is secured when the magnet is secured in that location. And then we use tracker to track the particles' attractional movement over time in both X and Y directions. Okay, and then using second order gradient from the original position via time graph, we can get the acceleration in each point and position over time. Okay, and at the same time, we have to account for water resistive drag forces of the particles, and then since it is above water, we generalize it as the particle is submerged like 1/2 into the water, and so therefore, with Stokes' law equation with our sphere radius, the water viscosity, and also the particle's velocity over time, we can get this, and then that's divided by 2 because it is half submerged in water. Okay, and then moving on. So after we determine the force from the coordinates we got before, we have to fit it with the acceleration to get a constant of c divided by its mass. The c was from before the magnetic moments correlation. And as you can see, the slope here for both the x and the y is very, very similar to each other, meaning our experiments were conducted, meaning our models predicted the coefficients very accurately. As you can see, both of them are included in both of them, their values overlap within the errors. So it shows there's a good correlation between the x and y graphs, which are measured independently of each other. And also the important thing is that we have to set the intercept at 0, because that's where when you have no force, you have no acceleration. So you have to intentionally set that at 0. Oh, okay. And then moving on, this is our actual comparison between our model and our experimental acceleration over time. All right, so as you can see from this bit, we times the originally coefficientless force with the coefficient we got from the previous slide, the c divided by m, and then compared it to the actual acceleration of the particle in the coordinates. All right, and then as you can see, we also inputted some error bars because the force prediction curve that we got was not exact with the actual positions of the f values. And as you can see, there's also some end deviations of the measurements, and I'll talk about them later. One of them is due to particles poking together, and the other one is also the reduce in force as you get very, very close to the magnet axis. So the first one we have to account for is bulk particles. What this means is that sometimes a lot of particles bulk together because they generate an induced B field after they get magnetized by the external B field, which is from the permanent magnet As you can see, this is a simple depiction of what is going on. So different particles, because of their induced E fields, they are attracted to each other in alignment. Yeah, so as you can see, this is how we accounted for that. So the B total is equal to the B external times the permeability of the vacuum and also the magnetization of the particles. And magnetization is seen as the number of particles, or to be exact, the number of atoms for the particles times the magnetic moment of the particles divided by the volume. And then at the same time, we also have difficulty predicting the force values when we are very, very close to the magnet. This is because as you get nearer to the magnet axis, for example, like over here, your potential energy peaks. And then what that means for this formula is that when it peaks, your derivative becomes zero. So meaning your force becomes zero over there. And then, so that's something we have to account for as well. Because, yeah. Okay, and then in conclusion, ferromagnetic materials have a visible motion, while paramagnetic materials and diamagnetic materials do not have visible motion because of their intrinsic properties. And also the force of attraction relies on the change in B, meaning its non-uniformity. And also the acceleration of each individual particle is, as you can see in our graphs, the correlation fits really well. So we explain it really well. And then also the particle alignment and the water drag is needed to be considered. And also the particles bulk together as you get closer to the magnet. So that's something we have to account for as well. And so because of that, we have some errors and then room for improvement as seen over here. Thank you.
Okay, thanks the recorder for this presentation. I just have to clarify the problem statement. The title of the question is strange motion. What do you think is strange about your phenomenon?
Yeah, so oftentimes we have different materials we can use. For example, in various videos, you can see that cereal or different materials that actually contain various ferromagnetic materials inside can move. And then people would think that's very strange. For example, cereal light can move.
But you're using ferromagnetic particle. It's pretty intuitive that it is attracted by the magnet.
Yeah, definitely. But,
do you think that the problem statement might actually be asking about the magnetic property of the fluid? How the fluid changes with the magnetic field you apply, and how that affects the particle motion?
The problem statement says that it is on the water surface. However, water is a diamagnetic material, and the diamagnetic materials, because its magnetic susceptibility is very weak, then that means it has no attraction, as seen in our motion, videos.
Alright, so you don't think the water deforms enough for the particles to move?
Because the whole thing asks for observed motion, and then there's no observed motion.
Okay, and do you have a close-up photo of how the particle flows on the fluid?
Close-up photo of how?
Yes. I have a question. Why don't the particles get pulled up by the magnet? How does it stay on the water?
Right, because of surface tension, and then also that is because we're measuring, we're accounting for, the problem statement asks for the motion of the particle on water, so that if the particles just fly up to the magnet, there's no purpose of measuring anymore.
So it is because of surface tension.
Yeah.
And you don't have a photo to verify how the surface tension of the water acts on the particles.
As you can see, particles are very, very small things, and then we have to use something even smaller than a microscope to observe the actual surface.
Okay, thank you. This is a yes or no question. Does changing the particle size and the particle shape affect your experimental results?
Definitely, but then that's mainly contributed to its density and its material properties.
Okay, last question. Why do the particles climb together when you don't apply a magnetic field? Okay, thank you. Thumbs up. Good morning, dear judges and fellow competitors. I am Arthur Shang from Team Miracle, and I'll be proposing problems of strange motion. So the problem statement says that sprinkles small floating particles on the surface of water in the bowl. Bring a strong magnet above and near to the water surface. Explain any observed motion of these particles. And I think what's really interesting about this problem statement is that it says we have to use a strong magnet, which we think is not explained by the reporting team. And we also think that the reporting team has to explain what is string without motion. And here's the overview of the report. For the phenomenon, they said that magnets attract ferromagnetic particles, which is very intuitive. And the particles tend to stick together because they are magnetized by the magnetic field. And for the theory, they said that magnetic force pulls the particles, and the torque from the magnetic field aligns the particles, and also there's drag force from the water that impedes the acceleration of the particles. And finally, in their experimental data, initially they tested different particles, and they chose ferroparticles to conduct their experiments, and they also used Python to plot their magnetic fields. So for the pros and cons, they provided intuitive explanation, and then clear graphs explaining the phenomenon. They changed the different parameters, the particle types, and they have good time management as well as a well-structured report. But for the cons, they failed to satisfy the problem statement, which we think is discussing the influence of the magnetic field on the shape of the water, and they do not consider the effect of the magnetic property of water. Some of the areas in their graphs were unexplained. The parameters were unchanged. For example, the particle size and shape. And their theory is still ideal. They did not consider the effect of the particles on each other because the particles may create dense in the water, so they may cluster together without applying external magnetic fields. And finally, they spend too much time on intuitive explanations using really complicated math to describe phenomena we already know. And there's a lack of error analysis. And points to be discussed. For the theory, we would like to discuss more about the problem statement, and we'll also discuss the effect of the magnetic property of water. For example, is the diamagnetic and paramagnetic properties of water. And also, we would like to discuss how the effects of particles have on each other without applying external magnetic fields. And why do particles stay in water? And what happens if we change the size and shape of the particles? Why don't all the particles clump into one dot? And how does fluid adhere to the particles? And for the experiment parameters, we would like to focus on the error on page 14 and page 20 and page 20. And we would like to hear the reporters' thoughts on possible alternative explanations for the error. And we would also like to discuss the importance of the observation of surface tension, which the reporter said is very difficult to observe because the particle is very, very small. And we'd like to discuss the reporter observed particle adhesion without the applied magnetic field. And we would also like to discuss if the reporter verified the magnetic field from the magnet. So I would like to begin my discussion. But first of all, did you verify the magnetic field from the magnet with like a Gauss meter?
Yeah, definitely. I didn't use a Gauss meter, but I used a magnetic probe, which is basically the same thing.
Okay, thank you. I need to know you verified the magnetic field. And can we go to page 14, please?
So there's a magnetic field over here.
Okay, thank you. Page 14. So, what's your explanation for the error on the graphs here?
Right, okay, so when we measure with different positions, obviously there's going to be error, and then keep in mind this gray curve is a prediction curve based on our potential energy plot points on the coordinates.
Yes.
So then this has to be a prediction. That's why it's a theory. That's why it is a model predicted by.
So, but what is the cause of the error? What's your explanation for the error?
The magnetic field probe.
The probe.
Yeah.
Okay, thank you.
But the error is very little.
Okay, thank you. Can you go to page 19? So you see, you said on this page that the correlation between your data and your prediction is quite clear, but I think the error here is very, very large. What's your explanation for this?
Okay, so first of all, this is measured at a very, very small range, so then this error is already pretty good. And then also, you have to consider that what we really truly want is the slope over here, which is determined at your c divided by your mass.
Yes.
Okay, so that's what you really need to determine over here. And then I can clarify why you're saying that there's some points over here that are low deviating. Is that correct?
Yes.
Okay, that's because for acceleration we use a gradient to measure the acceleration. So then, since at the start you can see over here, the motion of the particle is very, very it's a gradual motion. So then the acceleration is a little hard to track. So there are some small deviations. But in general,
so the deviation here is because the acceleration is very small, so the relative error will be large.
Yeah, yeah.
Okay. And for this part? For this part?
Yeah.
What's the error for this part?
Yeah, okay, so and this is where it is very, very near to the magnet, so its acceleration is super, super fast.
Oh,
and so
okay.
therefore there's only a few things we can track over.
Okay, thank you. Can you go to page 20? So your explanation for the error here is because the particles tend to stick together because their magnetic dipole are aligned.
Yeah, so is it okay if I draw? So let's say the copy of your magnet is S. Alright, so let's say over here, you have as you get closer, the radius of this area gets smaller. So the particles tend to become near to each other as you get closer. So then the particles are more likely to align with each other.
Exactly. Yes, I understand. But how does that explain the experimental data is larger than your theoretical prediction?
Okay, I understand. So since your B net is equal to your original external plus your induced, therefore that means that your B is actually increasing at a faster rate, meaning your potential energy differences is increasing at a faster rate. Therefore your force values would increase.
The force values would increase. So is this deviation caused by, according to your explanation, this deviation is caused by the error of the magnetic field provided by this magnet? Wait, I don't understand. How is this caused by the change in B net? Can you explain again?
Right, so for each particle, this is your external magnetic field.
Yes.
And then each particle, because of its ferromagnetic properties, each of its domains will align like this, right?
Yes.
Okay, and then that means that it will be equal to your B external.
Oh, I understand. So the
plus your induced.
also it's
And
more like it's more
particle bulking only occurs when it's relatively near to the magnet.
because it's strong. If the magnetic field is strong, there you positive. You need to align.
Also, the areas tend to be smaller around it, so that you can generalize that.
I also noticed that only some of the experimental dots have error bars.
Yeah, okay, I can explain that. I can explain that. As you can see, I have so many plot points over here, so it will be non-ideal for me to plot every single error bars over here because it will make the graph really unclear. So I just generalize into the front, the middle, and the end.
Okay, thank you. So now I would like to discuss the effect of surface tension. You said that the particles are not pulled up by the magnet because the water holds it together. So maybe the particles float on the surface of the water like this.
Yeah,
and there's a magnetic attraction towards there, and the water adheres to the particle like this. So the surface tension pulls it down.
Yeah, something like that. Yeah.
So okay, I think you should maybe observe this phenomenon to further explain your explain how this stuff will up in a magnet.
Oh, okay, sure. That's definitely we can do. Yeah. But then, however, I think by the problem statement is it's observed motion like typically on the water surface. So then that's something we need to consider, because if you try to account for how the magnetic field would pull this up and then overcome the surface tension, it kind of defeats the purpose.
Okay.
It just floats up.
So if this particle is closer to the magnet, the drag would also be smaller. Am I correct? Because it is pulled further from the surface of the fluid.
Yeah, but you have to consider that your velocity over here also decreases because the drag definitely decreases because as you get closer, your velocity is slower.
Okay. Do you have the theoretical data for the theoretical points for the effect of the drag, or did you include it as?
Oh, because the drag over here is included inside the prediction model. So like the yellow line over here. So it is included. So you can see from the prediction curve, and then also from the error.
Also, and could the error be also caused by the reduction of drag?
Yeah. So we accounted that over here. Over here, so you can see from the slide, it's the minus 6 over 2 pi radius times viscosity times velocity.
Can you go to page 20 again? What I'm asking is, because the acceleration is larger, could this be caused by the decline in drag force?
Decline in drag.
Yes, because the particle is further from
Yeah, but I think that would be kind of negligible compared to the effect of particles bulking. As you can see the curve. Yeah, so because particles bulk, the B is increased, and so your force is increased. That means your acceleration is increased for my prediction, for the experiment, but I didn't account for that.
And also when particles bulk, the affected area is still the same for the drag.
Sorry.
Because when particles bulk, for example, the first particles experience drag, but it blocks out the drag for the particles that are attached to this first particle. So it becomes like this particle may sway for the particles that are attached to it.
Yeah, but keep in mind, for each experiment in the model prediction, we're only predicting one particle at a time. So then we don't have to account for other particles, and then we can also,
And have you considered to change the size and the shape of the particles?
So we use magnetic powder, iron powder, and that's something that has around a radius of 10 to the negative 5.
Have you changed the particle size?
No, because they are variable.
So you haven't verified how changing the particle size will affect like the drag and how it gets polarized?
Okay, so particle size is something that changes its mass. Indeed, that is true. As you can see over here, the mass changes and the slope will change, the C will change. However, what really matters is its magnetic properties of the different types of particles you use. For example, like iron powder, it has its magnetic properties is a strong ferromagnetic material, while, for example, something like water or other oxides.
So like if you can change that, can you change the viscosity of the fluid to see how that affects the drag?
Change the viscosity of the fluid. Yes. Yeah, but then the problem statement suggests that we do it on water, and there's no reason for
so because you want me to use the problem statement.
Yeah, I'm following the problem statement.
Okay. And for this question, do you think it is possible for the particles to clump together without the existence of this magnet here? Do you think?
Yeah.
Yes.
Okay. All right. So each particle by itself, if uninduced by an external B field beforehand, then that means that its original magnetic domains are not in uniform alignment. So therefore, it shouldn't bulk.
Yes or no? Can the particles clump together?
It's possible, but then it's not very likely.
Not very likely.
Yeah. Because obviously some of them would have a general alignment, but some of them might not. So it depends on the particle.
Do you think it's possible that when this particle floats on water, for example, it goes like this? Yes. And maybe the water looks like this? And yes. And do you think putting this particle here, and because of the shape of water, the two particles will attract each other without the magnetic force?
why would you suggest they would attract together with non-magnetic?
Because you see, maybe like if these two particles are close together, then it creates a dent in the water. Then this particle should fall into this dent. It should attract. Do you think that's a possible factor?
Sure, but then I don't think that's the purpose of the question, because the question is asking if a magnet is set onto near and above the water surface.
Also, if you think the problem statement does not want you to consider the effect of the particle.
Sure, but this would be negligible compared to the induced reaction from the
Okay, thank you. So in our discussion, we discussed whether the reporter thinks the problem statement could be asking about the Moses effect, and the reporter this is how the shape of water changes with the applied magnetic field, and the reporter says no. And for the reporter says that the magnetic property of water and how the particles influence each other, the density of the particles, are really small, so that they didn't consider it. And why do the particles stay in water? The reporter says that the surface tension of the water causes the particles to stay in water, but they did not verify how the surface tension acts on the particles by taking a photo of it or doing any observations. And they didn't change the size and shape of the particles to see how it affects the drag. And why don't all the and for the experiment and parameters, the error on page 14 is explained because can you go to page 14? I'll explain because there's variation with the Gauss meter, and that concludes my discussion.
Thank you. So here I have a major question for both of you, and it's about the theory. So do you think that Moses effect should be considered in the experiment?
Could you elaborate on the
That's one of the characteristics of fluid. Should that be included in your experiment?
Yeah, so since water is a diamagnetic material, its magnetic susceptibility is very, very low and should not be considered.
It should not, or should?
It shouldn't, because the observer, you can't observe the water's dense because of, I guess, the Moses effect.
Okay, that's your opinion. And how about your opponent?
I think they should be considered because the shape of the particle caused the shape of the fluid caused the particle to accelerate.
Yeah. So for your experimental setup, so do you maintain the same height for your magnet in your experiment?
Yeah.
So how do you do so?
Yeah, okay. So as you can see, my clamp is over here and it is secured in that position when I drop the magnet. So it is constant throughout the experiment.
I see. So now I have a question for the definition of the problem statement. So can you define the strange in the statement?
Yeah, okay, so there's 2 points that are strange. First of all, oftentimes you can observe strange motion for different particles that intuitively, that originally don't look ferromagnetic. For example, again, I repeat, cereal, something like that doesn't seem magnetic, but intrinsically with its included iron particles within, it does make it attractive. And also, the second portion to that strange portion is because of magnets bulking together, as seen in this kind of situation. So I think that's pretty strange as well.
I see. So how about the opponent? Do you agree with what the reporter just said?
We disagree. The reporter said that the first thing that is strange is that that Cheerios tend to stick together. But if the reporter thinks this way, he should experiment maybe with Cheerios. And I think the bulking of the particles is pretty intuitive as well.
Yeah, I see. So here's another question for experiment setup. So for the water in your experiment, is that where's your water come from? The tap water or distilled water?
It's tap water.
So do you think the ions inside the water will impact the result?
Not really, because again, that kind of thing is negligible compared to the influence of the magnet.
Can you explain why it's negligible?
Oh, because again, I said water is a diamagnetic material, and a lot of the ions inside also do not contribute to that motion.
I see. How about the opponent?
Well, I think the ions could be paramagnetic, diamagnetic, or ferromagnetic. And because I think the Moses effect affects the motion of particles, I think the type of water that is used should be considered.
Yeah, we agree with the opponent side in this question. Thank you. judges, and we're the opponent. I'm the reviewer from Team Detonation. Today I'm here to review the problem of the string motion. So first is the topic and their focus. So we believe the focus should be what particle material will affect the results, and how does magnet create particle motion. Additionally, how some parameters influence the consequences. So here's what the reporter said in their report. So for the report phenomenon, when some powders are placed on the liquid surface and bring a magnet close above, the powder will have motions. And second is about the theory. The theory is about first, moment linearly proportional to magnetic field. And second, they assume simultaneous alignment. And for the experiment, they use different materials for the experiment parameters. And second, they use Python local gradient function and polynomial prediction curve. And third, the acceleration comparison is included and accounting for both particles in the experiment. So now our views on the report's pros and cons. So for the advantages, they have clear demonstration of the experiment procedure. And second, the stroke loss to analyze the results. And third, they employ 3D graph to illustrate their assumptions, and they put forward their prediction and compare to the results. And last, they discuss the possible source of the errors. However, for the places for improvements, first, they don't have enough focus on the fluid, which may have influence on the movement. And second, they lack of different parameters. And third, they fail to quantify the surface tension. And fourth, they only discuss one motion of the particles. And fourth, the lack of clear explanation for paramagnetic and diamagnetic. So here's about the opponent. So between the discussion, he talked about the pros and cons about the reporter, and the structure, and the question to the reporter. So here's what we think about the pros and cons. So for the pros, he has a clear understanding of the phenomenon. And second, he has precise conclusion. And third, he brought out several crucial questions about their theory and experiment, and also the problem statement. And for the cons, they have less discussion of the different motions of the particles. Here's the discussion, and the first one, the opponent asked, why does the experiment data have no error bars? And the reporter said, it's not ideal to put all error bars on the graph. And for our view, we think that all data should have error bars, so it should be put on. And the second question is, the opponent asked, changing the shape of the particles. And the reporter answered, the shape is something to change the mass. And in our view, we think that the reporter can try to control the shape of the particles and improve it in the future. And for the next question, the opponent asked, could the acceleration be caused by the drag force? The reporter said yes. And in our view, we agree with the opponent's idea. And the next question, the reviewer said, so it's my question. So do you consider Moses effect? The reporter says that no, it's not considered because it do not influence. And the opponent said yes. For this question, we agree with the opponent because that may affect. And next question, I said, do you consider water you used in the experiment? The reporter said they used tap water and the iron in it is negligible. And the opponent said it may affect the motion of the particle, and I think that's one of the things that have to be maintained so that it will not influence the result. And here's some pointers I want to point out. For the parameters, I suggest that the angles of the magnetic and the water used in the experiment and different shapes or sizes of the particles and also different magnetic might be included in their further experiments or research. And also, they might add error analysis to make it more reasonable. And there should be more discussion about the fluid. And second, their Moses effect should be considered. And last, surface tension when particles getting close should be considered. And this is the end. Thank you.
Some summary, we will conclude that ferromagnetic materials have a visible motion, while paramagnetic and diamagnetic materials do not have visible motion. And at the same time, with a few, we theorize that with potential energy, we can get the magnetic force. And then at the same time, there's multiple relevant factors, such as water-resistive drag forces, and also some different acceleration and with our exploration models. So I also want to clarify on what the opponent was talking about for diamagnetic material properties and also paramagnetic material properties. Since the magnetic susceptibility of these materials are for for diamagnetic materials it's 0, and then for para it's like 1,000 of the actual value. Compared to ferros more than 10,000, you can see that it basically contributes to no motion and no contribution to the phenomenon at all. And then at the same time, we also discussed various things. For example, that surface tension prevents the particles from flying up. But then, however, I think since it's asking about motion on water, so it's not relevant to the problem statement. And at the same time, we talked about how we measure the magnetic field, and I said it's used by, I measured that through the magnetic probe. And then I actually also did some error analysis. It's just, I can do all the error points. It's just there's no reason to do that because it would be very, very unclear for the graph. And also on particle side, I don't think it's very important because what truly matters is the material, which is what you want to test in this case. And then also, we also discussed how they particles bulk and clump together. Thank you.
Okay, excuse me, I just want to please turn to page 20. Okay. I think the problem statement just it's a motion of a group particles. Yeah, I'm curious about it. How did you analyze each one or the group of the motion? But that's not the most important because this is a two-dimension motion. I think that is not only the acceleration is we can understand the motion. So, but I think the most curious about it, what's the curve? The curve you can predict the motion. So what's your curve equation?
Curve equation?
Yeah, I'm curious. That I can predict the motion, you know. Versus the time, you can predict the motion different.
Yeah. So with our theory, we can calculate the amount of coefficient of force in the x direction and y direction with our curve prediction model from Python.
Yeah, but that's the magnetic field of the position. You know that I think I can know what each in different position. I can get a different force, so I can get the acceleration. But your prediction, please turn to the page 20. That's an amazing equation because can you show me the equation? Yeah, what's the function of the the acceleration of the time, the function of the equation.
The function.
Or how could you plot the curve?
The experimental or the model? Which curve?
The curve.
There are two curves there, right?
Yeah, not dots. The dots are experiment. But what's the curve? The curve, you mean the prediction?
It's a polynomial best fit that we got from the plot that I showed you.
So that's not theoretical curve? That's your fitting curve?
No, it is.
It is my theoretical curve.
Yeah.
And then I plot, it's a...
Yeah, so what's since you can plot the curve, what's the equation of the curve?
It depends on the position because the magnetic field.
Yeah, but this is the time.
Time means it's closing the magnetic field. As time goes on,
yeah.
it's closing the magnetic field.
Yeah,
the
but I
magnetic
think,
the magnetic field is stronger.
Because of the curve, you got the absolute value, So I'm just curious, how can you please show me the curve? How can you plot the curve?
Plot the curve of...
This is a record for individual particles.
Yes.
Yeah.
You're tracing it, the trajectories and measuring.
So you can see this is a curve, and then it's based on your x and y coordinate positions. So it's a function based on your x and y. And so if we can plug in the x and y...
Would you please show me the curve, the equation of curve?
Is the result.
It's a polynomial
Yes.
equation.
It depends on the position of the magnetic field.
Yeah.
That's why it shows, turns out.
Yeah.
Yeah, but I'm curious, you can predict the exact value of the acceleration into
This
the
curve
time.
predicted.
But I mean the curve he can plot. He can get the
He's like a one cloud is the position versus the magnetic field. That's the one.
Yeah, so that's the
You miss.
position of the magnetic field. Yeah, I mean that. But yeah.
The function
But
is...
also it's okay. Or the opponent review. What's your opinion
Well,
about
we
it?
think the way he plots the curve is he knows the force, so he could plot the acceleration. And using that acceleration, he could get in the next position. And using that next position, he can get the force. and calculates the acceleration of that position and calculate the next position and get the acceleration, calculate the next position.
Yeah, so would you please show me how can you calculate each position?
already done it.
Yeah.
Can I clarify? Yeah, so at each position over here, I have a potential energy on two of its adjacent locations. And you can find the middle point and its local gradient at that position to get F, which is the negative derivative of it.
So how about review? How about your opinion? Yeah.
My opinion on this question, we agree with what the opponent just said. It's the forces causes the acceleration, and then can predict the next placement of the particles, so that they predict.
I just have one question. Did you include in the drag force?
Yeah.
Could you turn to the page 14? I think you have a one. No. The next one you have the curve just yes, this one. Is there two curve or just one curve?
Oh, this is the x direction. That's the y direction.
Okay. How about the other one that goes up?
Oh, yeah. So acceleration and force is linear proportional. However, if you plot them together,
Is that the two curve or one curve?
this is x and this is y.
I know, but in one just x, is there two curve or just one curve? Is that I'm missing the yellow curve?
This is the model, like the theory prediction line, and then this is the experiment, and we're matching them together.
Time's up.
Thank you.
So, thank you. For the reporter, 7, 8, 8, 6, 7. Okay. For the opponent, 9, 6, 9, 8, 8, 8. Okay, then you have to explain later. Yeah, I would like to know. And the last one, the reviewer. 8, 6, 8, 7, 8. Please explain.
Okay, maybe I explain for opponent and reviewer. Yeah, because I didn't have time to ask question. Yeah, you two mentioned about Morse effect, and I didn't have the chance to ask you more to explain more about Morse effect. But during the discussion, I don't still get why Morse effect should be considered. And so discussion with component, I would suggest that you can explain more about your own opinion instead of just asking questions. Yeah. So actually, during the discussion, I don't get why it should be considered. So if you can explain more during the discussion, maybe you can get more points from my side. So this is why I do not grade too much points during the discussion with reporter. And also for reviewer, I don't see your own opinion. Yeah, so that's why I did not grade too many reports. Yeah, that's my.
Thank you.
Okay, thank you. And let's have a break for 10 minutes.